Okay. So right now we are having the opposing team, that is the string being theorists, to pose a question to the reporters. You have 1 minute to do that.
All right, we're having a lot of difficulty, but I think we would like to propose. Are you guys sure about this? Question 17. Quantum thingamajigaboo.
We accept.
I'm sorry.
We accept.
What is it called?
Quantum droplets, analogy to Bowman mechanics or whatever.
Yep.
Yeah.
Okay.
What's
This is the one I
question
wanted
number?
to see.
Number 17.
I'll unmute myself then.
Wait, I think we have time to.
Oh, we do have time to.
You're just ready to go.
Oh, okay.
There, buddy.
The number of this
That
question.
far behind
Yeah,
time.
you have time to decide whether you are doing this, or you've already decided.
We already accepted. I was just
Okay, so you have 5 minutes to prepare.
What is the number of the question?
17.
Do you all have access? I'm sorry, judges. I don't know if I sent you a link to all of the questions. Let me do that.
Yeah, that's probably fine because I think you guys usually tell us what the questions are, so it's not a big deal.
Mm-hmm. Oh, I think maybe Riley sent something.
That might work. That could totally like not be a good link at all. We'll see. Google Drive's always weird.
That link did not work for me.
Okay, I will share another link too.
By the way, that link will only show your own Google Drive.
Not to break the silence, but for those judges who are looking at the problem list and are thinking these are really cool problems, we definitely encourage you to share them with like the undergrads at your college if you think they'd be interested, or if you have friends you know who would want to work on these, because anybody from anywhere can compete for the most part.
Can you repeat that? Sorry.
I
Yeah.
was just telling the judges that if they're looking at the problem list and they really like it, or anyone really, if you really like the problem list and you enjoyed this, then definitely just like share the experience and let your friends know about it. So like next year, if they want, they can do it too.
Yeah, I think more people should participate. This is really fun, the discussion.
Yeah, we actually had 6 teams lined up, but just so much stuff happened in the last month that a lot of teams were like, this is too much going on.
The reporters still have 1 minute to prepare. And is Levy the only reporter, or is
Yeah, but Levi's the only reporter. Or unless Gonzalo, are you reporting too?
who is?
No, I'm okay. I'm super tired, sorry.
Yeah, I understand.
Wendy, Levi will be reporting, and the opposer has not been decided yet.
Okay. About 10 seconds, I recommend to start testing the sharing screen stuff.
Got it. Sharing that.
And you can
And then
start.
can you guys?
You can start.
Okay. All right. So hello, my name is Levi Roden, and I am presenting for the University of Washington for problem 17, which is using hydrodynamics of oil droplets as an analog for Bohmian mechanics, or some form of pilot wave theory. So as an introduction, there have been a lot of papers that have covered this so far, stuff like quantized orbits in specific radii, where the different radii that are possible is an integer, not multiple of an integer, excuse me. Crystal structures, where you can have a bunch of droplets that sit equidistant from each other. There have been some tests about single and double slit experiments run with it, and there have also been some other papers refuting it, but I included it here just because it is part of the discussion at least. And here in this presentation, I ran an experiment trying to recreate the particle in a box physics experiment, which is pretty standard in beginning QM. And also quantized orbits, especially as a way to help teach people quantum mechanics.
I'm using this speaker to
Disclaimer, I'm not a quantum physicist. Sorry, I was hearing some things. I'm not a quantum physicist. This isn't meant to be a commentary on actual pilot wave theory or how it pertains to the real world, because it is a very contentious topic. And I also believe that there's never really been like a wrong thing to study, even if the ideas don't prove to be 100% real. Always some cool math. Everyone always has fun. And that's why we're here. So my experimental setup, I generally followed a procedure laid out by Protier in his paper, her paper, excuse me. And I substituted silicon oil with mineral oil because I didn't want to spend $100 on the one they recommended. And I used my bass speaker as the vibrating plate. So here's a picture of my setup. You can see a petri dish with oil in it that goes up and down with the speaker. Here's like a side cutaway view of it. Inside, you'll see a plywood insert, and that insert lowers the depth of the oil in certain areas, and that can kind of guide where the particle wants to tend to go. In most cases, I just have the oil really low so it doesn't go out of there, but it still dampens the waves so there's less effects splashing back from the sides of the setup. So just to start testing it and work with how I was going to analyze data, I just made a droplet and let it walk across the surface, which is shown in this video. And what I had was an app on my phone that let me plot frame by frame where the particle was at each in that frame. And then it would allow me to export that data so I could analyze it later. Again, this is just a particle that I let roam around a circular corral. And when I graphed the velocity, this is the velocity vector, so it won't be negative in inches per second over time. We can see it dips down at different points, which you would expect if it was bouncing off the wall. And in fact, if you look at the acceleration graph, you see correlated story as you should, wherein you get these spikes of acceleration and then you get low to no acceleration as it travels in open space. A note here, the purple lines are the data I got just tapping the screen, and then in tan, I did a moving average of the last 5 points to try and smooth out any inconsistencies that happen because I'm using my phone and cell phone footage, which I can get at home. So going on from there, I set up a similar experiment to try and test the particle in the box. Theoretically, this should line up with quantum mechanical experiments where you have a probability that can be, in different eigen modes or that whatnot, where you expect it to stay in certain areas longer than in other certain areas. And sadly, when I ran the test,
Levi?
oh, sorry, how long was I cut out for?
Like for half a minute, I think. It's roughly
minute?
from.
So I just keep going. Go to
Yeah. You didn't miss a lot.
Cool. So this was the video I took from the particle in a box experiment, where I just cut a little rectangular area in the middle. And it didn't turn out quite exactly as I wanted it to. The position graph showed a pretty linear correlation. It doesn't really look like it stopped or slowed down in certain places, which you would theoretically expect if there were nodes of where it hung out and nodes where it tended to skip over. And the velocity, I think, is pretty consistent throughout this whole thing. And the acceleration bobs up and down by 0, which means there's no real change in pace. And I think all of these lead to point to the fact that this model does not really exhibit particle in a box behavior. There are many different possible reasons this could be. It could be that my setup was imprecise. Again, it is just a base speaker. Another possibility is the droplet couldn't properly walk with such a small enclosure. I won't get too into it here. Feel free to ask about it later though, but it is very specific conditions where the droplet will walk with a constant velocity. Otherwise, it tends to have less predictable behavior. And also, in my research, I found after the fact that particle in a box hasn't been recreated by other scientists either, suggesting that it might just be a shortcoming of the model as a whole. So the next thing I decided to test was quantized orbits, where you can have 2 particles and they will stay in certain distances from each other. I thought it would be fun to test and cool to see, but also I thought it could help me consider some different avenues for this model, whereas a lot of people are talking about the possibilities with it as in its own right as for explaining quantum mechanics and whatnot. When I figured out that I could actually do this in my dorm room, I thought it might actually be kind of cool to see if this would be a way to help explain some weirder parts of QM to people. So I took a look at that. This is my video of the quantized orbits, of the quantized orbit that I took my data from. It's a bit hard to see the droplets, I'll admit. You can see them best when they cross over the green grid lines in the back. And if we graph the data, we can see that their distance stays actually a phenomenally, I think, constant distance apart. And here at the end, one of the droplets actually broke at the very end. So my personal hypothesis is that the variation at the end was leading up to that event and would, I think, be more chalked up to the experimental setup than the model itself. And in the same paper that helped me create the experimental setup, they proposed this mathematical model for those distances where n is an integer and e sub naught is a constant. just to set up the first distance apart. And then it's multiplied by the Faraday wavelength. So the model ends up creating these standing waves that have that wavelength. So essentially, the idea is that these two are sitting in the troughs of their combined waves as they bounce across the surface. And that's what gives rise to these quantized orbit distances between the particles. And I just thought this was super cool because there's kind of not, when you look at the fluid bath, there's not so much an inherent quantization of it. But yet it still gives rise to these quantizations, which I think better than any mathematical expression can really give students an intuition of why the quantum world is quantum in its core. Even if you're looking at it and you say, well, open space isn't really that quantized. And so I think for that way, it's good. And anyway, thank you guys for listening. I want to thank Amanur Rahman. He let me and Gonzalo interview him in our research for this project. And other than that, I yield my time.
Perfect timing. So have the opposing team decided who is the opposer?
Yes, I will be the opposer.
Okay, so opposer, you have 2 minutes to ask questions to the presenter.
Cool. Could you open up your PowerPoint again, please? You're also muted, by the way. So my first question is, how did you make sure that the orientation was steady, it was level with respect to horizontal?
All right, so I will try and get the screen share, but it wasn't really in the presentation. So to do that, again, that was outlined more in the paper I was referencing mainly. But so I first did it with a bubble level just to get it as close to even that way. And then what you can do is you can tune it to where Faraday waves are generated on the surface. And then from that, you can tell if they're starting in one corner or the other. You can fine tune, and I just used index cards to fine tune the angle of the whole setup until it became an even wave all at one point.
Gotcha. Did you experience any spatial dependence of the emergence of Faraday waves? Were they appearing on the outsides before on the insides or anything of that sort?
Generally, if I got it perfectly right, which if I'm perfectly honest, it was very hard to do in the setup, they emanate just in rings. So it'll be a flat pool, and then all of a sudden you just get rings around it, and then they'll degrade into a more chaotic structure, I suppose.
Maybe I missed this, but what frequency did you operate your setup at?
I used 80 hertz.
80 hertz. And what was? How did you standardize the size of your droplet?
So also a shortcoming of the experiment. Current research, there's a bunch of fancy piezoelectric generators. I just had to use a chopstick. In general, to get it to walk, you have to get it to a very fine size, so that almost selected the size for me, but that is definitely a shortcoming.
That's fair. That's fair. Did you try to produce crystals at any point?
I did not try to do crystals in a scientific way. I made them, but I didn't take the time.
So the opposer, you have 3 minutes to prepare your presentation. Proposer, we have 10 seconds left. You can start sharing your screen.
Let me know when to begin.
Okay, you have 5 minutes to present.
Okay.
Timer starts now.
Cool. Hello, everyone. I'm Siddhant representing UC Berkeley, and I'm going to be opposing the problem just presented, which is problem 17 about quantum droplets. And let's get started. So firstly, the problem itself we're familiar with. We're supposed to investigate the nature of these mysterious droplets of oil that emerge on vibrating fluids and their analogy to quantum mechanics. Now, the good things about your presentation and the things I really admire are that you picked a paper and you stuck to it and you really investigated the depths of it. And also you focused on qualitative intuition for the theory instead of modeling in equations and such. That was quite nice. For the experiment, I'm very impressed with the results that you've got, especially the quantum chorale, which I found for myself particularly annoying to reproduce. And though the particle in the box was a bit so-so, but the walking and stuff was quite well done. Also, good job on leveling, because that takes a hell of a lot of time. In terms of presentation, good visual aids, good presentation, good organization, and of course the acknowledgement of resources is all good. Now let's move on to the meat of the matter. So first of all, it turns out the thing you labeled as quantized orbits was actually the initiation of the crystal, and so that was not actually the quantized orbit. So maybe that's something you're incorrect for. Furthermore, in terms of theory, you could probably explain the analogy between Bohmian mechanics and this droplet a bit more, because we do see the direct connection that there's a wave and there's a droplet, the same way in Bohmian mechanics there's a particle and there's a wave guiding it. But some equations which directly illustrate the dynamical relations between these two systems would have been appropriate to help us see the connection. Also, further setups that you can explore with the system is, you say particle in the box was hard to reproduce, but it turns out some papers can actually have shown this by using ferrofluids, injecting ferrofluids into the droplets beforehand, and using magnets below the dish, and so you can create spin systems which display these behaviors. Now, some future suggestions and discussion questions for you to potentially look forward to. You can try the magnetic and rotating dish systems that I just discussed. The good thing about these systems is that they actually display the quantized behavior that you were looking for, especially with analogy to the particle in the box. Scattering. You said you got the scattering, but it was actually the crystal. So you were kind of mischaracterized that. But I think with your setup, it should be easy to get scattering too. All you would need to do is create two potentials that lead into each other, and then you should be able to get them in quantized orbits. And crystals are particularly good to produce in this system. Now, the issue is the main point of the question was to study entanglement and Bell's inequality. And I feel like that's been completely left out. The question was essentially focusing on how far you can push this analogy to cover things like Bell's inequality, whether those violations are still consistent within this classical analogy or not. Now, I grant you that that's a very hard thing to do, but if you take a look at the paper that I recommended to you, which is about magnetism and rotation of the system, you can actually produce those spin state systems and get them entangled. And once you get them entangled, you can actually test Bell's inequality. Now, I'll leave the rest for you to discover on your own, but one more thing that could be interesting for you to do is explore these regions that have been well documented. If we do at some point get standardized way of producing your droplets, you can explore the various regions in which the droplets' behavior changes and how it depends on frequency. For example, in some frequencies, the walking regime, for instance, only occurs when the bounce of the droplet is half of the frequency of the water itself. I need to be right below sub-Faraday threshold, and there's optimal radii of the droplets for that to occur. So exploring that would be quite useful for showing your cause. And if we go back to the problem for a sec, just to make sure we're not getting lost in the weeds. I do admire that you have tried to produce as many quantum analogies as possible, but you did bring up the double slit experiment. And it turns out that the one paper that was able to produce the double slit experiment did it incorrectly, and every other source that's tried to produce a double slit experiment using the setup has shown that it was actually a bimodal distribution that was mischaracterized as a double slit experiment. And so maybe you want to look into that and redo your experiment, or maybe do an experiment to confirm that the double slit does not actually work with this. And the main reason there is because if you had discussed the analogy to Bowman mechanics, what you're saying is that this is a local theory and it can't capture the same behavior that you need for it to capture to reproduce something like the double slit experiment. It does capture single slit diffraction, which you rightly said. So that's cool. All right, that's
Yeah, our
about it.
time is up. Now it's time for the opposer and reporter to discuss. We have 5 minutes.
So I believe I did mention that there was a lot of contention around the double slit experiment, and that I included it because in my research it cropped up, and I thought that it's under contention, but I think it's still important to the discussion of this model. So like I said, I left it there. I left the asterisk, I think, that said not necessarily true, but I think that while it is the point of the, I also agree, I read and saw the papers about the other quantized orbits you were referring to. I considered that, and I said I thought that was too difficult to run in the setup. Again, a lot of it comes from I'm running it in a bedroom in an apartment, and
Yeah,
I
I've been
do
in the
not
same
have,
place, yeah.
yeah. I did do a lot of research. I left it out for brevity about the walking and how you have to get the droplet has to bounce at half the period of the speaker to get the walking motion. And I did study that, and I felt like there's plenty of research on the before regions, and also that was less quantum in nature. So I excluded it. Other than that, spin also, looking into it, very difficult to do, needed a lot of precise laboratory conditions to run, as well as droplet size. And I figured I would rather focus on doing something that I could do, that I felt I could be proud of presenting and could help something move forward, as opposed to try and do Herculean research tasks.
That's totally fair, and I do appreciate all that you have actually produced, but I do still have the question though. Since the prompt focuses ultimately on whether you can produce Bell's inequality, with your experience, can you make a guess and give some reasoning on what you think about the matter? Would you be able to produce the Bell's inequality violations using a setup or not?
I personally don't believe it would be very easy, especially in the time frame I had to do it with my resources and what I have access to. The question also said specifically to go to as many different analogies as we could. So what I really chose to focus in is I tried to focus on more of the analogy part, what I thought could be applicable to people who have our resources and wanted this as a window into the quantum world, as opposed to how specifically perfect can I get it to that quantum world.
Okay. On that note, did you experiment with various sizes of dishes? Did you compare different sizes? Because we personally tried out 3 or 4 different sizes of dishes and multiple frequencies and different subharmonics to see what exactly the behavior is, and we tested out all those regimes. So what kind of process did you go through to optimize this bouncing or walking or any of the behaviors?
Walking, essentially.
No, did you just explore the parameter space and get a sense of the behaviors of the droplets in various
Yeah. So I tried multiple different frequencies, and then you have to test the amplitude to get that as close to Faraday waves without breaking the surface as you can. And also I tried many different containers before I shelled out money to Amazon to get Petri dishes. And then most of my parameters from once I got it set up that I knew could work was the different plywood inserts for different corral shapes.
Speaking of plywood, did you ever try to construct potentials with these? Because from what I tried and what I know is to construct potentials, you create barriers just below the surface of the water, and so they act like potentials. But the way you created potential was scraping off some of the wood, which is a very interesting difference from what the research currently does. So could you explain the reasoning behind that and what kind of results you saw with that?
So what I just did is the plywood is meant to be the place that you don't want the particle to go, right? So I just took the plywood and I cut a circle out of the middle, and then that circle had deeper level of oil, which allowed the droplet to stay in there.
So you were literally trying to create like a potential well right there.
Okay. Well, the idea is that the oil then is too thin over the plywood to let the droplet bounce. But then there's enough oil there that the waves will be carried across it, so you get less reflection into the droplet corral.
Okay, when you talk about the quantum corral, and the interesting thing about that is depending on how you orient the surface, you can get the high, like peak probability density to move around within the corral. Did you experiment with that? Did you try to like see how you could orient the surface to like configure the Faraday waves in a way such that you can control where the central, like highest probability density will move around?
I did not do that except for regards for trying to level it.
Okay, that's fair. That's fair.
That,
Yeah,
that would be
this-
cool to test.
Definitely, yeah. Okay, cool. Exactly on
Okay.
time. Wow.
From
Oh.
now on, all the team members can join the discussion.
I'm betting Miguel has a lot of questions.
Yes, I have a lot of questions.
Yeah.
So so my first question is like, okay, so I understand your motivation to create this this potential well. But what do you think the experimental limitations are, or what the theoretical limitations of this particular model are? Like, why do you think that you actually didn't observe um, the behavior that we would have expected in this case?
So if like reflect with respect specifically to the particle in the box, I do think it was the corral was just a lot harder to get the exact conditions I needed for droplet walking in. More broadly, it's the model has interesting pros and cons. I don't know how much you guys have read, like if you've read the non-specular, I think is the word reflection paper and stuff, which is all just like super interesting, whereas they look into it more, the specifics are breaking down, if that makes sense. So where on the surface you might see some cool quantum-like effects, when you dig down into like the math and specifics, it starts to break down a bit.
Yeah,
Did
so
you-
I guess like my question is like, why would this necessarily occur? Like, is it something to do with the fact that the pilot waves, as they pass over these potentials, begin to damp off? Is that a potential reason, or like something such as path memory? The fact that as these waves propagate throughout the system, some of them reflect off the container and then also influence the actual behavior of the walker as time goes on. Like, do you think like any of these kind of things would necessarily limit your experiment?
Yeah, I think they would. And I think, again, that's what the goal of why I had the plywood in there was, that you have that little strip of, hopefully this will dampen the waves so that if stuff reflects back, it's less. But also that's just the thing where you're like, it'd be really nice if I had an infinite plane of mineral oil.
So I have a question. So you were talking about how you entangled particles, and you were asking about
No,
Bell
we entangled.
inequalities.
We found a paper that entangled.
Oh, okay.
Yeah, yeah. We found a
So-
paper that actually injected the droplets with ferrofluids, placed a magnet underneath the dish, and they were able to produce quantized orbits and stuff. And there was displaying, yeah,
Perform the
Yeah.
experiment. Okay.
yeah. So those were. Sorry, what?
Oh, I was going to ask what, or maybe to Levi too, because I wasn't on this project. What was the realization of the Bell inequalities? How was that done?
Yeah,
I don't
so
think it was done here.
Yeah.
But in,
So we were
yeah.
actually trying to push further like this experiment. As we didn't have like the resources to do it, we actually contacted one of our applied mathematics teachers and tried to like use his formulas and his mathematical models he used to predict like how particles will interact between each other and collide. When we were doing this, we were not actually able to reproduce any valuable data, as the equations he gave were like experimental. But we tried to push this as far as we can using simulations.
I have one question though. Okay, so the issue was you kind of misidentified lightly the quantized orbits, which were actually just crystals. Now, my issue is in the quantum analogy, what quantum phenomena have you actually produced? Because walking and the bouncing is fair enough, but that could easily be labeled as a simple hydrodynamic thing. What's a one-to-one quantum mechanical analogy that you have fully developed? Because the particle in the box didn't work for you, right?
Yeah. Again, I don't even think the argument is so much one-to-one. It's that you can have a non-quantized system give rise to these quantized values and quantized states.
But your states weren't quantized. As I said, what you said were quantized orbits were not actually quantized orbits. They were just.
Well, they were a quantized distance apart.
Are you sure it was
Uh,
quantized? Because I know for a fact that you can produce them at varying distances, just by
Yeah,
definition.
well, I mean, they're
it's just
different.
that they were just stable floats, but they weren't quantized.
Siddhant, did you like make an experiment that actually did this? Like maybe you could explain how you went about doing this.
Oh,
Yeah.
I can actually
I'll
talk
elaborate.
about how to produce these quantized orbits. So in what the
Yeah, but
like
you only have 10 seconds left. I recommend.
Okay, that's fine. That's fine. 2 seconds, you said?
But they were quantized. They were different integer distances apart. And you can move
How
up
do
like
you know the integer distances though? You didn't. Okay, maybe you should figure out a way to like measure that or like formalize that, because right now you're making a claim, but it's not fully backed up.
Okay, so it's time for the reporter to have the closing remarks. You have 1 minute.
Okay. So first I want to thank everyone for talking about it. It was actually just really cool to have a bunch of people who had read papers and knew what they were talking about. So in conclusion, I feel like I showed that particle in a box, at least when you're building it in a college apartment bedroom, is not too feasible an experiment to run. As well as through the discussion, I think we talked about how a bunch of stuff can break down, and how the model is not as perfect as we had hoped, 10 years ago. But again, I do really believe that this is a way that you can show people that in a system that is not necessarily broken up individual bits, you can end up with these systems that exist in certain quantized states, whether that be the orbits you were referring to with spinning corrals, or whether that be with two particles orbiting each other at these set distances. It's just, I think it's a great way to show people, and when you can do it with the speaker, pretty cheap way to say that, hey, this weird math you're learning, there is there's a way you can get some sort of intuitive. Time's up?
Yeah.
All right.
Okay, so I'm going to ask the judges to give their remarks.